we think so. We have this theorem saying that if we have a homomorphism, this function as a homomorphism from a group G to group H, what we can then say that actually if we take any, and this will apply if we take any two elements, let's say GH from the group G, then we have that under this homomorphism function, so phi of G will equal phi of H for these two different elements GH from the group G, from which the homomorphism will go to H. And of course these H's are different. H, lowercase h belongs to G as well, like lowercase g. And phi is the function defined in homomorphism, also being the homomorphism itself. So, alright, so we have this thing, and that's equal to, alright, so there's an equivalent statement regarding this. It's equivalent to saying that G times kernel phi, which is a subgroup by the way, alright? We might focus on that in another one somehow, but it's equal to kernel of phi again, multiplied by the left by that h. So phi of G equals phi of h if and only if G multiplying the kernel phi equals h multiplying kernel phi. And these are instances of cosets, where we have one element from G multiplying everything in kernel phi, because kernel phi perhaps has more elements. In non-trivial cases, more than one element. By the way, kernel phi is a subgroup. It can have more than one element in general sense, in general cases. So this is a coset. It has a set of more elements. This also. So these two sets should be equal. And now let's prove it. The way we'll prove it is by equivalence statements. So if these two things are equivalent, either we could do implication from here to here and here to here. Here we can. There's more ways one can prove it, but let's stick with this following way. We'll write equivalent expressions until I'll start from here and get to here. So we'll make some reasoning. We'll write equivalent expressions until we get from here to here. So let's start. This thing says that the let's coset of kernel phi by some element G is equal to H. That means G and H are both in the same coset. They create the same left coset. Well, that means that if we take, let's take some x in the kernel of phi. If we take some x from kernel of phi, then this thing should be equivalent. So we'll take this statement. So I'll write this, so separate. We'll basically be doing the proof from this side, and gradually we'll get here in a second. So I say that some x in the kernel phi. Alright, so it's of course going to be an element of G via chain, of course, reasoning, but now we look at it, of course, furthermore as x part of kernel phi. That's important for us. Let's say that, and now we know G times kernel phi equals H times kernel phi, the same left cosets. So we can express H as G times something from the kernel phi. So some x, so we could choose x from kernel phi. So actually, yes, in the left coset. So G times x, there's some x that and whether if we use a dot or nothing, I mean the same, the group's operation, whatever it might be. So Gx equals H for some x from the kernel phi. Because we have these same left cosets on both sides of this equation. But this also says that because I can say that I can multiply by H inverse on both sides, so I can sort of have H inverse G times X equals identity, I can denote by E. Well, if X was in kernel phi, and it's a group, by the way, kernel is a group, I mean, furthermore from this reasoning, we can also say that happens if and only if H inverse G is inside the kernel, actually, kernel phi. Alright. So as we see, by the way, we should have written this equivalence here. Our goal here is to take this initial statement and do equivalent expressions until we gradually get to this. That's a valid way to prove equivalence. So we do many equivalences until we actually get straight to here. Well, yes, why could we go from here to here? Well, there's small ways to view it, but basically if you have something, this whole thing multiplying kernel equaling to identity, what I can also say is multiply by x inverse on the other side. But if x is in kernel and kernel is a group, it must have inverses, so x inverse is there as well. So x inverse equals to this, and therefore this equals to x inverse. X inverse is in kernel, so this is in kernel. So yeah, this is in kernel. But if something is in kernel, then under the homomorphism function phi here, it should actually be equal to the identity. And by homomorphism rules, we can write this out as phi of h inverse times phi of g. We can take out the two elements now, h inverse and g that we have here. That should be equal to e. I mean e as identity. And that equals still to e. Alright? So I can either write the equivalent expressions, or I can just go to the next slide and just say, okay, I'm just now rewriting sort of with the basic homomorphism rules. And we're slowly getting very close to here. Now you can see, we can take out the inverse outside the homomorphism, and also a rule here. So phi h and the whole thing inverse times phi g is identity. But at that point, we can multiply by phi h, not inverse, phi h itself from the left on both sides. So we get phi g equals, and we'll get on the right side phi h. So we, by the way, by these equivalent expressions, got all the way to this side of the expression. So yes, we proved it.